Welcome to Mr. Hobbs AP Chemistry class. Today is Wednesday, November the 30th. Okay? Do what? Oh, please subscribe to this channel.
You demand it. Subscribe.
All right. Now, today we just need to make sure that we just answer any questions that we have about bonding. Make sure that attractive forces, IMFs, Coulombic attractions, everything about ionic bonding, metallic bonding, covalent network, covalent molecular. We need to know it all. Okay? So, this is the time to ask questions. This is the time to, figure out and get anything that you don't know figured out. So, why does CaF2 have a higher melting point than NH3? What type of compound is CaF2, Anthony? Ionic. Whereas somebody else, tell me, NH3 is what? Covalent molecular. Okay? So what is holding, when we melt it, what is CaF2 going to break up into when you melt CaF2? Ions. So what do we have to overcome in order to melt it? The lattice energy, the Coulombic attractions, the lattice energy. And how do we measure that? Coulomb's law. Product of the charges, ladies, product of the charges divided by the size. Okay? So, versus NH3, it's covalent molecular, so what forces do we overcome there? London, what else? Dipole, what else? Hydrogen bonds. How do I know it's got hydrogen bonds? Okay, Macy, say it again. Has nitrogen and hydrogen. Now the hydrogen has to be directly attached to the nitrogen, oxygen, or fluorine. And in this case, it's going to be, because that's all there is, NH3. So we do have all three IMFs. But how do IMFs compare to ionic bonds, covalent bonds, or metallic bonds? Much, much weaker. Okay? Much weaker. 10 to 100 times weaker. Okay? So we always say they're the kindergartners compared to the adults. Of the kindergartners, hydrogen bond's the strongest kid on the playground. But it's still weak compared to an ionic bond, a covalent bond, or a metallic bond. So if you're comparing melting points, ionic bond is always going to be greater than an IMF. Covalent molecular substances in general are liquids or gases, and that's the sheet that I just gave out to you. They're generally going to be liquids or gases at room temperature because these IMFs are weak. So at room temperature even, there's enough energy to break those bonds. Now what's very important, as you know, is that the nitrogen to hydrogen bond is not broken when you boil or melt NH3. You break the IMFs, the molecule to molecule. Always remember, ionic compounds, when they melt or boil, they're breaking down into ions. Metallic, they're going to break down to the metallic atoms. Covalent network, what's the diamond made up of? Carbon, what? But what's the individual particle making up a diamond? If this were to melt, if you melted a diamond, it's going to break up into carbon what? Carbon atoms. Covalent network are made up of atoms. They don't have molecules because they're just one big, huge network of atoms covalently bonded to one another. So it breaks down into atoms. Whereas covalent molecular, when you melt it, melt ice, or you boil ammonia, what does it break up into? Molecules. Okay? Covalent molecular, go figure, made up of molecules. Ionic compounds are made up of ions. So when you melt them and boil them, you're breaking them down into those fundamental particles. Covalent network are atoms covalently bonded, so they're going to break down into atoms. So that's kind of a key factor to always just keep in mind. So it's got a higher melting point than ammonia because CaF2 has more masses, has longer, stronger London forces. No. Do London forces even apply to CaF2? What do they only apply to? Covalent molecular. Okay? CAF2 exhibits network covalent bonding. No, that's not one of our 5. CAF2 is smaller and exhibits greater coulombic attractions. Well, it doesn't have to do with the size. CAF2 is an ionic substance, and it requires a lot of energy to break up an ionic lattice. And that's compared to ammonia having to break the weak IMFs. Even though it's got hydrogen bonds, it's still way weaker than an ionic bond. So that's a key factor. Which of the following pairs of elements is most likely to create an interstitial alloy? Remember, we have 2 types of alloys. What are they? Substitutional, interstitial. What are the size of atoms, the size of the metals, and substitutional? About the same. Interstitial, one is significantly larger than the other. So how do we know this? We don't know the sizes. What do we look at on the periodic table? You can look at atomic mass. You can just really look at how far apart they are. But remember, transition metals in the same period really are all about the same size because they all have that 4s2. Then you're adding the 3d. So transition metals are very similar in size in the same row. Okay? So you want to look at the ones that are farthest apart, kind of in rows and have more energy levels. So which has the bigger difference? So interstitial, we want a big difference. Which one's got the biggest difference? Aluminum, which is 13, and lead, which is 82. So there's like 4 rows difference between them.
Is there a lab test in the year or the semester?
We'll probably have one more quiz on thermal.
And then we start the labs and stuff.
Yeah. Yeah, I'm hopefully going to get at least one more lab. Huh? Okay. Now, why can a molecule with a structure NBr5 not exist? We talked about this 10 times yesterday. Nitrogen's not big enough. Okay? It can't have an expanded octet. It only has 2 energy levels. Cannot have an expanded octet. It's got to be on row 3 or below. But that's not the answer. The answer is just big enough, small, or it's too small. Too small to have an expanded octet, or it's big enough to be able to have an expanded octet. All right, so go to number 8. Did we already do some of these previously? Okay, but let's just talk about it again. How do we know which one has the highest lattice energy? Coulomb's law. So whenever you're dealing with ionic compounds solely, you compare with Coulomb's law. Product of the charges divided by the size. So this is plus 1 minus 1, plus 2 minus 1, plus 2 minus 1. Does it even apply to this? Because what type of substance is this? Covalent, right? So it doesn't even apply to that. So comparing to here, so now we have, obviously this one is plus 1 minus 1, so it's less. So it's going to be between these two. So then what do we decide there between these two? Size. We want the highest, so what does that mean about, we want the smallest. So magnesium is smaller, magnesium is smaller than calcium, chlorine smaller than bromine, so it's going to be the magnesium chloride.
There's not going to be one like.
No, it's opposing. They always make it real obvious where one's bigger and smaller. And a liquid, its molecules are held together only by which of the following would be expected to have the lowest boiling point. Lowest boiling point, what state would it probably be in then? It's probably going to be a liquid or a gas. Okay? Lowest boiling point, what does that mean about attractive forces? Okay, so you might even want to write in here, as far as a note to yourself, lowest boiling point always means weakest attractive force. And then obviously the converse, highest boiling point is always going to mean strongest attractive force. Because that's what we have to look at to determine this lowest boiling point. That always has to imply weakest attractive force. So, which one's going to be the weakest? Ionic, London, hydrogen bonds, metallic bonds? London. Which is going to be the greatest? Ionic. And between these, ionic and metallic, they're kind of, you're not ever going to have to compare those. Those will both kind of be, depending upon which metal it is. Because tungsten has a super high melting point, so which means it's got super strong attractive forces. 10, the 6 carbon atoms in benzene molecule are shown in a different resonance forms as 3 single bonds and 3 double bonds. If the length of a single carbon-to-carbon bond is 154 picometers, is it pico or pico? and the length of the double carbon bond is 133, what length would be expected for the carbon-carbon bonds in benzene? So since it says resonance, what does that mean about the bond?
It doesn't matter what order.
It's shared. It's somewhere in between, right? So the bond is going to be shorter than a single bond, but longer than a double bond. So here's your double bond. Here's your single bond. So where should the resonance bond be? Just somewhere in between. And the only one that's in between is 140.
Okay, so it doesn't matter the actual length in between? Like, so it doesn't have to be the average of those
No.
two? Or...
No. And you don't need to know the actual length or anything like that. You just need to know that it's going to be somewhere in between. And then which of the following lists the species of order increasing boiling point? So raise it up just a little bit for me, camera. So again, increasing boiling point, what are we looking for?
Attractive forces.
Okay? Strength of attractive forces. Okay, now Reese, I want you just to give other people a chance to say the answers out. Okay? Well, you say them so fast, nobody has a chance to think about them. Okay? So, attractive forces. Which element, or which compound, which substance stands out here as far as being different? NH3. Why NH3? It's got hydrogen bonds. Okay? So what does that mean about the strength? It's going to be the strongest. And then hydrogen and nitrogen. If you have a diatomic element, two atoms, what's the difference in electronegativity going to be? Difference in electronegativity is going to be 0. The same electronegativity, so the difference will be 0. So what does that mean about the type of bond? Non-polar covalent. So diatomic molecules are always going to be non-polar covalent because the difference in electronegativity is 0. It's a perfect sharing of electrons because they both have the same pull for it. So what's the only type of attractive force then? What's the only IMF? London. With what do London forces vary? Okay, if you say mass, you're not getting any points. Okay, we've got to get that out of our heads. That's how we look at it. We can determine it quickly, but the answer is always going to be the size of the electron cloud, the number of electrons in the electron cloud, okay, which is directly proportional to the mass. But AP will not give you credit if you say mass, because it's based upon the electrons in the electron cloud and the polarizability of that electron cloud as it distorts. So we know that increasing, we want the least, is going to be A, hydrogen's the least because it has the fewest electrons, then nitrogen, and then because ammonia has hydrogen bonds, it's going to be the greatest.
Could we have just said that we knew ammonia was going to be the most, so we just went ahead and picked A?
Well, yeah, but I mean, that's good test taking, but you need to know why as to the other two as well. Okay? So now we go to number 22. Okay, once again, highest boiling point. What type of substance are all three of these? Well, just in general. Covalent what? There's two types of covalent, so I'm always trying to specify. Molecular, you got covalent network, covalent molecular, so we're always going to put the second word on the covalent. Okay? So we're going to be looking at highest boiling point, we're looking at strength of attractive forces, IMFs. So, what differentiates these? The hydrogen bonds. Okay? How do we know? Somebody else hadn't said anything. How do we know that it's got hydrogen bonds?
Hydrogen's attached.
The hydrogen attached to the oxygen. Okay, I wasn't sure what were you all the thing that you guys were saying? Phone. Oh, okay, phone. Okay. I just is what I heard. Okay, phone. So, but the hydrogen attached. So the OHs. So we have the hydrogen bonds. So can this form hydrogen bonds? No, because the hydrogen's not attached to the oxygen. So this is going to have the weakest. Now between these two, how do we tell? This one has two places. Okay? And so this is your ethanol alcohol. This one boils actually around 78, 79 degrees Celsius. This is your fingernail polish remover. Okay? This is, evaporates very quickly. And then this one is antifreeze, ethylene glycol. We did the density lab with this at the very beginning of the year, and it was a little bit more viscous, a little bit more gooey. Okay, and we use it as antifreeze because it boils at a much higher temperature than even water. Okay? Do what? No, as you guys said,
sitting on the scale, it was evaporating.
yeah, right, because it just has weak IMFs. All right, next one, 23.
When you use the charts, do you want to read on the chart?
Yeah, what's question 23 say? Then read it.
Or highest
Highest vapor pressure. Again, pressure is dependent upon what? What? The weakest force, but number of moles of gas, right? So if something has a high vapor pressure, that means there's a lot of moles of vapor, there's a lot of moles of gas, which means that is it evaporating quickly or is it evaporating slowly? Quickly. So what does that mean about the attractive forces? The weakest attractive force. So highest vapor pressure is always weakest attractive force. So if you want to put that again, it's just in the notes on the side there. Make it, that's always just a good relationship to know. Higher the vapor pressure, the rate, that means it evaporates quickly. Weakest, so which one? We already kind of said it. Acetone. Okay, so what's the next one? 24. Which one's going to be the most soluble? Now, what determines that? Solute, solvent, and that's how the hydrogen bonds. Okay, so which one's going to be most soluble? Why, Wesley? Because two places for the water to attach, you're going to have a much stronger solute to solvent attraction here. So when you have this, you're going to have a high solubility. This is still very soluble in water. Alcohol is very soluble in water. But this is going to be even more soluble because of the two places. And then this one is only going to be mildly soluble.
It's because which of the substances would be soluble?
Which of the substances would be soluble? Okay. Did they say all of them?
That's the one that's like rolling.
Okay. This one, I mean, there's a chance that the hydrogen can attach here and make it, but acetone's not very soluble in water.
Yeah, it says that it has permanent dipoles.
Yeah, but it's very, this one's solubility, that's going to be, if it's soluble, it's going to be very limited solubility. Okay, because we do have a polar part right here. Now, what's the shape going to be around this carbon? Trigonal planar, right? AX3, trigonal planar. So it's going to be bent around the carbon. The CH3s are going to come down. CH3s are going to come down like this with the oxygen up at the top. This is a polar bond here. So we have a little bit of a dipole moment, a little bit of polarity, positive, negative, which is what they're saying allows it to be soluble in the water. I'm never going to ask you anything that ambiguous, though. It's going to be more obvious like this than something that's completely nonpolar. Okay? 25. So here's a formal charge question. On structure A, the formal charge, what is it on sulfur? +2. What is it on this one? 0, right? So which one is a more preferable Lewis structure based on formal charge? B. Okay? Now, let me just say this. If the question simply said, draw the Lewis structure for, I think that's an SO42- ion. Draw it this way. If it doesn't say anything about formal charge, don't worry about formal charge. Just draw it according to our normal rules and whatever. The only time you have to draw a formal charge is the question specifically asks for it. Okay? Otherwise, just do it with the normal Lewis dot structures and don't worry about it. What is the molecular geometry of structure A? AX4, so it's going to be tetrahedral. Now, how are you going to know that tomorrow? You just have to have it memorized. Hopefully you've been working on it some because you try and cram it all in tonight. It's not all going to stick. Okay? And then what is the SO bond order and strike? What's the bond order going to be here? Now, they're saying that you can do resonance on this one because the double bonds could not only just be here, the double bonds could be here. So therefore we have resonance. So if we want to get the bond order, we could go 2, 3, 5, 1, 2, 3, 4, 5, 6. Somehow I was getting 7. 6, okay? 6 bonds in 4 places. So 6 fourths is 1.5. Or you can realize that the double bond is being shared between 2 spots. However you want it, however it makes sense to you. Okay? So because of resonance, then what do we know about the bond strength, bond order, bond length, all the bond characteristics? They're all going to be the same. Okay? Because of resonance. All right? What's the next one?
7.
What's 28 say? Which of the 5? Well, we just did this. All bonds are identical. So 29?
No, I was going to say, is A not also, like, why is A not necessarily true?
Because it's a tetrahedral shape. Still, it's still AX4. So it's not opposite. So they're all equal. So 29?
There are 4 statements. You got to
Okay. Okay. Which structure is more likely to correspond with the actual Lewis diagram for the sulfur? Okay. Structure A, single bonds are more stable than double bonds. Structure A has the most unshared pairs of electrons. Structure B, there are more possible resonance structures. Structure B, fewer atoms have formal charges. Okay? You always just want to minimize formal charge. Minimize formal charge. That's going to be the thing. It's, all this other stuff is not really any of it's true. Then 30, we already kind of did this. The greatest pressure is going to be the greatest number of moles. So what you have, this is 20 divided by 4, so that's 5 moles. This is 40 divided by 20, so that's 2 moles. And this is 30 divided by 30, which is 1 mole. So the one that has the most moles is going to be the helium, so most moles is most pressure. Now that's flashback. That's a good review for the exam. Now this is the reason why I wanted this one. Which has the greatest IMFs? That's what they said the answer was? Well, they're 100% wrong. Oh, assume ideal. Okay, if they have ideal behavior, then why would they all be the same? Because, no. What's the question asked for, Justin? It says which strongest IMFs. So you have to deal with IMFs. Ideal gases don't have IMFs. Now, let's just talk about real gases, because I don't see this as being an AP question with like that. Real gases, which one's going to have the strongest IMF? Why? Why NO, Cameron? Are there hydrogen bonds here?
No.
It's got nitrogen and oxygen, but what what doesn't it have in order to be able to form a hydrogen bond? It doesn't have hydrogen. Okay? So we'd have to have a hydrogen attached to one of these in order for it to be. But we are going to have a polar bond. And in addition, what about electron cloud? Which has, it's got the largest electron cloud, so it's got the strongest London forces, plus it's got a dipole moment, meaning it's polar. So it's got both strongest London forces and it's got dipole-dipole, so it's going to be significantly stronger IMFs than these. Now between these two, which is going to have the stronger IMFs? Why neon? More electrons. Both only have London forces. Okay? All right, free response 2. It's just going to go to a third. It's just it spreads out. It's going to decrease by 2/3. It's going to be a third of the pressure of what it was. All right, CO3 2 minus. Now I look at that, I automatically know if we're looking at Lewis structures. CO3 2 minus has what? Okay? CO3 2 minus. It's not. Coach Pate made it not follow me. They still can't see me. Yeah, they can. Maybe. So we have 24 electrons. So we put our carbon, oxygen, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So what do we do when the central atom is electron deficient? Okay, we have to steal from the rich, share with the poor, form a double bond. Now which one do we take? So what does that tell you immediately? Resonance. Okay? So we form the double bond, so then our resonance structure could be here, or it could be here.
If we're doing resonance structures, do we still need to drop the...
The answer is yes. You do need to put the brackets around them as well. Okay, so what's the bond order going to be between each carbon and oxygen? 1.33, 1 1/3 approximately. Okay? What do we know about the bond length and bond strength of all three carbon-oxygen bonds? They're all identical, equal in strength and characteristics. Well, how are they going to compare to the length of a double bond? A little bit shorter than a single bond, a little bit longer. Okay? Make sure we just understand all that about resonance. So then CO2, and y'all, we need to know everything and anything about CO2. That is the one thing that they use in AP all the time. So you want to go through and you want to use, what's the shape going to be? Linear. What's the type of hybridization? SP. Is it polar or nonpolar? Why? Because it's symmetrical. Okay? What type of hybridization? Oh, I have that. Okay? So just everything about CO2. What's the molar mass of CO2? 44. Y'all, the more you can just know about CO2, that way you don't have to draw it, you just know it, just everything about it. Ammonia is another good one to know, but CO2 they use in everything. So, the carbonate ion is formed when carbon dioxide reacts slightly with basic cold water. Draw the Lewis dot structure for the carbonate ion, include resonance. Now, I think I showed you the question from last year where they just said, they gave you the description that the bonds were equal and two of the bonds were the same and one was different. So they kind of were implying to you about the resonance. They didn't say draw the resonance structures. They wanted you to see that there were resonance structures. So if you're drawing Lewis dot structures and you have resonance possibilities, go ahead and always draw them. Better be safe than sorry. It doesn't take that much time. Okay? Draw the Lewis electron dot structure for carbon dioxide. We did that. Describe the hybridization of the carbonate. What is it going to be on carbonate? sp2. Does everybody know how to figure that? It's AX3. Okay? So there's 3 electron pair domains. AX3. 1 plus 2 makes 3. Okay? And then describe the relative lengths of the 3 carbon bonds of carbonate. They're all equal. Compare the average length of CO bonds in the carbonate to the average length of CO. Well, CO is double bond, so these are all going to be slightly, which one? Longer or shorter? Slightly longer. Double bond's going to be shorter. These are going to be slightly longer than the double bond. Anthony, focus. All right, number 3. Cameron. All right, so this is a good one. You got all kinds of information, so you got to go off the chart and base your IMFs off the chart. So we look at the boiling point. Which one has the highest boiling point?
Chlorine. Oh, yeah, chlorine.
Okay? Chlorine's got the highest boiling point. Bond length. Okay? Why would chlorine have the longest bond length? It's just the biggest one. It's just the biggest one. And then here, the bond strength. Okay? Why is nitrogen going to have the strongest bond strength? Triple bonds. What does oxygen have? Double bonds. Halogens and oxygen have single bonds. Okay? Now, so the bond strength of nitrogen to oxygen, triple bond versus double bond. The bond length of hydrogen to chlorine. Why is hydrogen so much shorter? It's just way smaller. The boiling point of chlorine versus oxygen. What are we overcoming? What do London forces vary with? Size of the electron clouds, the number of electrons in the electron cloud. If you don't say that, you're not getting credit. It's not the mass. Okay, because that's what we look at. That's what everybody, the other problems say that. Oxygen, water and ammonia have nearly the same molar mass, da-da-da-da. Well, that's telling us that they have nearly the same London forces, but the answer has to be electrons in electron cloud. Okay? Use principles of molecular bonding to explain why H2 and O2 are gases. I love this question. How can hydrogen, which is a gas, and oxygen, which is a gas, make water, which is a liquid at room temperature? Hydrogen and oxygen as the gas are both what type of substances? Covalent molecular, polar and nonpolar. So what's the only type of attractive force? And since they're very small molecules, they're going to have very weak London forces. So they're the weakest of the weak. So at room temperature, there's plenty of energy to keep them apart. So they're gases at room temperature. But when they bond and form water, now water molecules exhibit not just London forces, and what about the London forces of water? How are they going to compare to the London forces of hydrogen and oxygen? Stronger, because now we have a bigger molecule, more electrons. But now also we have what else? What else? Dipole-dipole and hydrogen bonds, which are much stronger IMFs, which cause it to be a liquid at room temperature, requiring much more energy to break the molecules apart. Great question. This is one that you can just baffle your friends with on a Friday night conversation. Do you ever wonder, how can hydrogen be a gas and oxygen be a gas, yet they come together and make water? How can that be?
Well, here, let me tell you.
Yeah, that's right. Guys, don't impress the girls with your knowledge.
Are we having math problems with this?
Nope.
So it's just a bunch of short answers?
Yep. Yes. Hydrogen is just way smaller than chlorine, so the bond length is going to be way shorter. Okay, stay with me. I left it over here. Okay. Now, in preparing, listen, we got 8 minutes. In preparing for the test, I just gave you a chart with all the different properties of the substances. You need to know and be able to identify the properties of each of the types of substances. Okay? Yeah. I mean, that's what we've been talking about for the past 2 weeks. Is all the different, what makes an ionic compound different from a metallic compound, different from a covalent network, different from covalent molecular, polar versus nonpolar. Obviously, you need to be able to identify if it's polar or nonpolar. So you need to be able to do all that. You need to know your shapes, your angles, bond angles, and your types of hybridization. That's just some straight-up memorization, but it just is what it is. You need, just remember, group 3, thank you. Group 3, they form exceptions to the octet rule. So if boron or aluminum are in the central atom, they're only going to have 6 around it. Expanded octets, we say that the elements have to be on the 3rd row or below, but what's the answer? Why can phosphorus have an expanded octet, nitrogen not? Nitrogen's not big enough.
We're going to have like a free radical thing.
Possibly. Okay, shh, y'all. The question is, what do we need to know about sigma and pi bonds? Now, you should be able to recognize, we know that the first bond between any 2 atoms is always a sigma bond. So if it's a single bond, it's a sigma type bond. We also know that if it's a double bond, you're going to have a 1 sigma, 1 pi. If it's a triple bond, you have a single and 2 pi's. Only p orbitals form pi bonds. Okay, shh. Hey, you guys, back row. Now, obviously we talked about it. You need to be able to recognize resonance structures and know everything about resonance structures. You need to be able to then determine hybridization. Big thing is you need to be able to compare melting and boiling points. We did that some here. But if I want to compare CH4 versus NaCl. Back row. I can hear you from here. Highest boiling point or highest melting point. Which one's going to be higher and why? Why NaCl? Ionic versus covalent molecular. So it's going to be that one, because ionic is always higher. So the IMFs here, what's the IMF going to be on this one? Only London forces. Okay? If we wanted to compare HCl to H2O. Why H2O? Because hydrogen bonds versus HCl, HCl is going to have what? Dipole-dipole, and they both have London forces. Now, whose London forces would be stronger? HCl. Okay? Because it's got more electrons in the electron cloud. Okay? It's a bigger molecule. Okay? So, I mean, we look just practically, we just say, okay, this is 36.5 versus 18. But because it's 36, it's going to have more electrons in the electron cloud, so it's going to have a stronger London forces. Okay? So the practical aspect is we look at the molar mass. But the answer we write down is more electrons in the electron cloud. Okay? If we wanted to compare NaCl versus NaI. Okay, I'm hearing both. Okay? Along with all the chatter, even though I've been begging back for the back row to stay focused. Okay? Trying to help y'all get ready for this test. Okay? Is it NaCl or is it NaI? I've heard both. What do we use? First off, both substances are ionic. So whose law do we use to determine? Coulomb's law. So if ionic compounds, you go to Coulomb's law. So it's product of the charges, plus 1, minus 1, plus 1, minus 1. So then we look at the size. Cl is smaller than I. Since in the denominator, that means it's going to have a stronger lattice energy, which means it's going to take more energy to break it apart. It's going to have a higher melting point. Okay? And then lastly, if I did Kf versus CaO. Kf versus CaO. So notice again on something like this that it's a plus 2 minus 2 versus plus 1 minus 1, and the Ca is bigger than the K and the O is not bigger than the F, but we look at plus 2 minus 2. Yes. Okay, so we should be able to identify solubility. We should be able to identify differences in melting points. Again, remember, ionic always trumps covalent because of much stronger attractive forces.
So you have no asymmetrical?
Most definitely.
So covalent, you think it's going to apply how many electrons?
If it's nonpolar, the London forces are based upon the number of electrons. Then dipole-dipole. Hey, what's the trend? What's the trend in electronegativity? Smaller going down, bigger left to right. So if we want to compare dipole-dipole attractions, remember it's the more polar, which means the bigger difference in electronegativity. So we don't have to have the electronegativities memorized. So, but the bigger the dip, Justin. You're just making noise. And okay, listen. the bigger the difference in electronegativity is going to be the farther apart they are physically on the periodic table. So the farther apart they are, the bigger the difference, the more polar they are, which means the dipole-dipole attraction will be stronger. So if you're going to compare, say, CLF to IF, if they combine together, well, IF is going to be a bigger difference in electronegativity than CLF is. So as a result, it's going to be a more polar molecule. It would have a stronger dipole-dipole attraction, even though it's kind of an iffy molecule. IF would be an iffy molecule. Okay. All right.
He always has to explain.
Yeah, I know. You guys are sitting there saying, what's he talking about?
Sometimes I just trust that it's true. Everyone should start on.
Any last minute questions? Anything that's fuzzy?
What kind of short answer type of things do we need to know? Just like
That whole packet of questions is a great resource.
Will there be anything similar to that?
Well, solubility, all the IMFs and all that stuff. Okay?
If you have to break this down,
Well, there's just a lot of chemistry. You got to go through thought processes. That makes it harder.